Hello, everyone. My name is Víctor Arniella from the University of Oviedo in Spain. I am a member of the Situ research group. And today I'm going to present our first results regarding crack growth rate tests under in situ electrochemical conditions. This is the outline of my presentation. Let's start with the motivation of the work. We all know about the importance of studying hydrogen enrichment. Today, I want to focus on steels for hydrogen storage. In vessels, due to changes in temperature or pressures, we have cycle loads, and in presence of smart cracks, these cycle loads can provoke crack propagation. And in a hydrogen ambient, this hydrogen can move to the crack tip and enhance that propagation. So it's very important to study crack growth rate in hydrogen ambient. To do so, the ideal procedure is to perform tests under in situ gas condition. It reproduces a real service condition. You can select the pressure you want, but the equipment is quite complex and expensive. So to reduce cost, an alternative is to perform the test under in situ electrochemical condition. It's simple, it's cheap, but it doesn't reproduce the real service condition. You have to find the parameters that reproduce that condition. In a previous study of our work and in collaboration with the Institute of Poitiers, we have evaluated the crack growth rate of a chrome-molybdenum steel under in situ gas condition. Here we have some of the results. So today, the goal of this presentation of this work is trying to obtain this behavior that was obtained in gas condition, but with electrochemical methods. To do so, we follow this methodology. We perform crack growth tests following the ESDM standard using SMB specimen of this geometry. These parameters, we use a pre-crack with this value, a load ratio of 0.1, initial stress intensity factor average of 30. And to obtain the crack growth rate versus delta K curves, we use an extensometer that during the test is measuring the COD. For the air test, we use the atypical 3-point bending device here. And for the in situ test, we inverted it. Okay, so here you have the device. We invert it can't use the extensometer because if not, it's in the liquid. And here you have a picture of a real test. Regarding the test condition, we evaluate two different ambients as we're using two different electrolytes. A saline electrolyte, 3.5% of sodium chloride, and an acid one, is more aggressive. That is a solution of sulfuric acid and oxyarsenic. We use different current densities, 0.2 for the saline electrolyte and 0.5 and 1 for the acid electrolyte. I want to say here that also in previous study, we measure the hydrogen that we introduce with this condition and 3 hours of cathodic charging. 3 hours because it was enough to saturate the sample. And also we evaluate different frequencies. In air, we use 10 Hz, and in hydrogen from 1 to 0.01 Hz. So results, we use a 42CRMO4 steel, quench and temper at 700 degrees for 2 hours. The microstructure is a tempered martensite with carbides. Here you have the chemical composition and some properties, the hardness, the strength, ultimate strength, the soundness, and the diffusion coefficient. As I told before, this steel was already evaluated, but with in situ gas condition. And in that study, we have observed that in hydrogen ambient, the crack growth rate increased, it's like 10 times faster. These tests were performed with CT specimen. So the first thing that we wanted to know is if the geometry has an influence on the results. So here you have the CT specimen, the air test, and here you have the SMB specimen. It's the same. So we assume that there is no influence of the geometry in the results. Regarding the in situ test, let's start with the saline electrolyte. First, we use a density current of 0.2 and 1 earth, because in the in situ gas test, we have observed that with the 1 earth frequency, it was enough to see embrittlement, and also when we reduce the frequency, the result was the same. So in gas, the frequency has no influence. So that's why we started with 1 earth. But in the in situ test with the saline electrolyte and the electrochemical condition, for 1 earth and 0.2 milliamp per centimeter squared, the result was the same as for the air test. So we decided to reduce the frequency. When we reduce the frequency for the saline electrolyte, at the beginning we have a little embrittlement, the gradual rate a little faster, but the slope comparing with the gas test is lower, and at the end the behavior is the same as the air test. So we decided to increase the hydrogen activity of the electrolyte and start using the acid electrolyte. We use first a density current of 0.5 and a frequency of 0.1. And at the beginning, the result was the same as the gas test, but then during the test, the gradual rate is almost constant, or it increased a little bit. We decided to increase again the hydrogen activity by increasing the density current, but the result was the same. Okay, so it looks like for a same electrolyte, the amount of hydrogen you generate is not important, at least in this range of delta Ks. So what happened here? We think that the problem is with the surface absorption kinetics, that it seems that it's faster in gas and in electrochemical condition, it's slower. That's why we can maintain the same behavior during the test. To prove this, we prepared a new batch of experiments using the acid electrolytes, the density current of 0.5, but different frequencies. So we give time to the hydrogen to introduce in the sample. So these are the 4 conditions that we used. Let's start with the red, the dark red, let's say. The result was this. So for 1 earth, we have embrittlement at the beginning of the test, but during the test, the gradual rate is constant. And at the end of the test, the behavior is the same as for the A test. We decrease it to 0.1. This is the curve that we already showed you in the last slide. We reduce it more to 0.05. And the same, at the beginning, the result is similar to the gas test, but the gradual rate, it's constant, the gradual rate. And when we decrease it to 0.01 earth, the result was the same as for the gas test. So when we want to evaluate steel under electrochemical condition, it's important, or it looks like you have to reduce significantly the frequency to obtain same values as for the gas test. Also, we observe the fractal surfaces for the air test and for the in situ test that are similar. On the left, we have the CT specimen. In the air test, in both, we were able to see the striation lines typical from this kind of test. And in the in situ test, with the condition that it's similar to the gas test, the fractal surface is exactly the same. We also have this comparison. In this graph, we have a ratio of the gradual rate in hydrogen and gradual rate in air. And you can see that up to from 40 to 80, the behavior is the same. The gradual rate in hydrogen is like, 13 times faster. And we were able to have the same behavior as for the gas test. So conclusions, just to conclude. Electrochemical media generates a lower hydrogen concentration in the crack front region during the test, resulting in less enrichment compared to tests in hydrogen gas. Higher current density increased the hydrogen content in the steel, but hardly influenced the fatigue crack-out rate results. However, electrolyte selection has some differences, obtaining higher crack-out rates for the acid electrolyte that is more aggressive. Frequency turns out to be a key parameter in situ electrochemical hydrogen charging tests. The lower the frequency, the higher the crack-out rate. And by using an aggressive electrolyte and reducing the frequency considerably, similar values were obtained for the 42CRMO4 steel under electrochemical and gaseous condition, being the surface absorption kinetics the determining factor of the process. That's it. Thank you for your attention.